of all, I'll talk about derivations, and that I think I'll do today, obviously, and the modular differential. And this will really be the topic of the first lecture. Then I talk about the conormal sequence, and the rank of the modular differential. This is the modular differential. And I'll talk about ramification locus. I think this may be, hopefully, the second lecture. And we'll go, and the singular locus may go to the third lecture. And then I'll talk about conjectures, these famous conjectures. And this will be already the fourth lecture, the conjecture. So this is 2 and 3. And this is the first. And here is already the fourth one. And I talked about the complementary module. And I introduced the free difference. And this will be the fourth lecture. And in the fifth lecture, I'll compare the difference. And also, I don't only compare difference. I don't only compare them, I also relate them with the conductor and with the socle and with the Jacobian ideal. And this is the fifth lecture. Obviously, if I have time, but I'm afraid I won't have time, this is really the new material, and this is joint work with Ulrich. And in this paper, which is not unfortunately submitted, though it's written, we do actually compute the difference. And we see when they are equal, in more general case of this, and we compute it for classes of ideals, like for determinantal ideals and things like this. And we get efficient formula in that case. It's very easy formula in that cases. And I'll try, hopefully, and this has several applications, so I'll try to talk about this if I get to it. So my purpose is really to cover the classical thing. So let me start. And I'll start with number 1, as I said, so I don't rewrite the title. So let's define first what a derivation is. This you should know already from any algebra class. But as I said, I should say that I usually speak very fast. And it's not a good idea. So if you don't understand me, or I'm going too fast, please stop me. I'll try to write everything in the board anyway, but stop me. And you'll get lecture notes. So you can, you don't have to take notes. You can just listen if you don't like taking notes. Okay, because you'll get lecture notes. Okay, so R is a ring, and we put more assumption later on when we need it, and M in our module. And then a map D that goes from R to M is called a derivation if he has the following two properties. First, we want it to be, a group homomorphic, so to be x plus y is dx plus dy. And second, we want it to have the Leibniz rule, or product rule, which is simply that dxy is x dy plus y dx. Okay? So you should have these two properties. And now let's give some example. So a very easy example is the trivial map. Okay, that sends everybody to 0. is a derivation. And there are rings for which this is the only derivation, like Z of R, okay? The Gauss integer. It's easy to prove it as an exercise in algebra. And then another example, very important, is the polynomial ring. Let's say that K is a field, okay? Then the usual derivative are a derivation. So these are the partial derivatives. So you find a polynomial and you take the partial with respect to itself. Okay? Now, I wanted to see what are the properties of this derivation. And an important property is actually quite important, is that the kernel of any derivation is a subring. So this is really different from what happens in the case of, you know, a ring homomorphism, when you know that the kernel is an ideal. So this makes a big difference. And why is this true? But you know that, I mean, it's easy to show, but the important thing is that one is in the kernel. Okay? And you can just see it applying this. Okay? So if you want, I can write it down, but this is very easy. D of 1 is D of 1 times 1. You have seen it is D of 1 plus D of 1. Okay, so now I want to talk about a derivation. So yes? Oh yeah, I'll do everything characteristic 0. And you will see, but anyway, this is true, but it doesn't matter because here it's just a group of morphisms, it's just cancellation rule. So that works in any characteristic. But later on, I'll do characteristic 0. For the moment, this doesn't need characteristic 0, but when I'll tell you when I'm in characteristic 0. This doesn't need anything. So now, let's take, so as I said, I want to consider R as an A algebra. So I take A another ring, and I take a ring homomorphism. This makes R an A algebra, okay? So and now, what do we do? I want to notice the following thing. So, first of all, D of A is in the kernel of the derivation if and only if D is a linear. And this is exactly when, what does this mean? And this is, so the definition of being derivation a linear means exactly that it fixes A, okay? So practically the elements of A are constant. And this happens, so we call that D is a linear, and this happens exactly if PDA is in the kernel of D. I'm going to show this in 1 second, very easy. Second of all, every derivation, and this if you want to take it, the definition of a linear is really that and we call it an A derivation. If this happens. Now, one important thing about, so here I want to say that every derivation is a Z derivation. Which is clear because one is in the kernel and the kernel is a ring. The mass contains Z. So this is clear. Okay? Just use that one is in the kernel and the kernel is a subring. So now, so if we have an A derivation, another thing I want to write here, is you get that the kernel is not just a subring, but is a subalgebra. There's an algebra over A containing algebra. Okay? And now the first thing, so I'm going to prove one, but the proof is very easy. And the first thing is that if I want to compare two derivations, this is going to be very important, I'll use it a lot. I want to compare two derivations and tell you when they are equal. Okay? And if I have two A derivations, they are equal if and only if they act the same on the generator of R as a algebra. So two A derivations are equal if and only if they have the same value on the generating set of R as an A algebra. So, without writing too much, let me tell you why 3 is true, and then I'll write down one. So why is 3 true? The point is that to check that two things are the same, you can just check that their difference is 0. Okay? So this just means they are equal if and only if d1 minus d2 is 0. But d1 minus d2, the difference of two derivations is a derivation. It's easy to see that the difference of derivation is a derivation. So we want to show that the difference derivation, d1 minus d2, is the 0 derivation. So how do we show that? That, remember, we just have to show that the kernel is everything. So the kernel of the difference, because these are A derivation, is an A algebra. Okay, is an A subalgebra of R. But d1 minus d2 are 0 on the generating set of R as a subalgebra, because they have the same value. So if d1 minus d2 are 0 on all the generator as an algebra, and they are an algebra, they are equal to R. So the kernel is R, so d1 minus d2 is exactly equal. So let me erase there. I just write just one thing. Oh, where is the eraser, guys? Okay, I don't know. Here? Yeah. Oh, I see it. Thank you. Thank you. So let me do this. So 2 is obvious, I don't say anything. But for 3, observe that this is an A derivation. And the kernel of d1 minus d2 is all R. That's it. Okay? So this is the 0 derivation. That's what we wrote. And now I have to prove 1, and I have to prove that to be an A derivation is the same. Remember, this is if you want to take it as a definition of a derivation, you want to prove that it's the same as being A linear. And this makes sense because A derivation really means that A are a constant. So let's see that that is true. So I have two directions since I have an equality. So D of AX, that is an element A in A, is equal to dA of X, because remember, that's the way multiplication acts on R, through phi, that's as R is an A algebra. And now, this is equal, just apply the Leibniz rule, d of A dx plus x d of phi of A, okay? But now, this is equal, this is 0, because if you assume that, phi of A is in the kernel, and then you get just phi of A of d of x. Okay? So, which is the same because of how the multiplication is defined as A dx. So indeed the A comes out. Now, so it's A linear. Now let's see the other direction. Assume it's A linear, then for every A in A, you have that d of phi of A, okay, is the same as d of A times 1, okay? But this is the same as A times d of 1, which is 0. So it's constant on A, okay? So this finished the proof. And now, so we have defined this A derivation, and I can take the set of all of them, okay? I can take the set of all derivation, and these sets of all the A derivation form a module, an R module. So this is the set of all A derivation. And it is an R module. Okay? And what it is exactly all the set of the D from R to M such that D is a derivation, is an A derivation. Or is a derivation over A. Okay? And in particular, if you take M to be R, then this is just called the derivations of R. Okay? This is called the derivation. This is actually very important module. And we, for example, with Ulrich and others of Siemens, and we study and we use it very much to study, question of Poincaré about curves that are left invariant. And they were usually studied from the point of view of, of differential geometry and of analysis. And we instead came to the problem using commutative algebra. And the idea was exactly to encode all, the vector fields that leaves a curve invariant as this module. So this module is very important, to study, okay? And its property. Unfortunately, it's a very difficult module to study. Very, very difficult. Okay, so first of all, there is one case where it's easy. So let me tell you the easy case is when R is a polynomial ring over A, then you can take the partial, like I said before, and each of the partial is a derivation, okay, of R over A. And what's happened is that actually these guys, let me call it delta I, generate the modular of derivation, and the modular of derivation is free. So this is, so this is the basis, okay, as in R module. So let's prove it. I mean, the proof is very easy. We are going to use this property 3 that I told you is very important. So to show that something is a basis, it's enough to show linear independence and generating, okay? So first of all, generating. So I take any derivation. Okay? I want to express it as a linear combination of delta I. So now I consider this particular derivation. So this is my D, and I evaluate it at x1. Okay, so I get an element in R. I multiply by delta 1, and so on. This is an element of R. Remember, because D is a derivation, it goes from R to R. This is an element of R, so this is just a linear combination of the delta. So this is obviously a derivation. Okay? And now we claim that these two are the same. How can we prove that two derivations are the same? I told you already, check that on the generating set as an algebra, they are the same. But the generating set is x1, xn. Apply xi here, you get dxi is equal, delta 1 on xi is 0. The only one that is different from 0 is delta I, and is 1. So you get dxi delta I xi, which is 1. And this is the only one. So they are equal. So you just use that proposition and they're equal. Okay? So this is still not the proof. Okay? Of this fact. So these are the same, so it's generating. Is this clear? Okay. Now I want to say that they are linearly independent. So I'm taking, like you do in linear algebra, a linear combination of this guy, and I assume that it's 0. I want to show that the lambdas are all 0. Okay? But then I just apply this, so this is obvious derivation, call it delta, and apply this to xi. Is equal lambda I. Okay? But this is 0, so this is equal 0. Okay? Just have to evaluate the lambda. The delta are all 0 except for delta I, and then you get lambda I. Okay? Okay, so now we have shown this fact. So it's one case we compute the modular derivation, but don't get spoiled. It's really very difficult to compute. Okay? So instead to compute the modular derivation, what we do, we focus on something else, which is the modular differentials. Okay? So this is difficult, and so we look at the modular differential. And you could ask, how are these connected? How do you go to this guy? What is this guy? It turns out that the dual of the modular differential is the modular derivation. Okay? So we call this there, you remember? The derivation will call, and I'm defining this omega. And what turns out, what's the link, is that of omega against r is exactly that. Okay, so that's the link. Okay? And you could ask, so the dual of this guy is this guy. So we somehow study the modular derivation through the modular differential. And you could ask, is the converse true? Is the dual of the modular derivation the modular differentials? And the answer to this important question is no in characteristic P, and in characteristic 0, is still unknown. This is basically, I mean, under some assumption, this is the so-called, and we'll talk about it later, the Zariski-Lippmann conjecture. And it's a very, very hard problem, okay? Because if we knew that this guy is the dual of this, for example, when this guy is free, this guy would be free. And unfortunately, we don't know that, okay? So let me now, before I go and talk about this, the modular differential, tell you a remark that is going to be very important. And then, actually, we are going to use it throughout the 5 lectures, so it's very, very important. And then I go on to talk about the modular differential. I must ask, because I am very bad with time, that you stop me. I don't want to go over time. I don't want to. This is already a long lecture, so please stop me if I'm going. When I'm close, you can just tell me. Okay. So before I want to tell you this remark. So this is a crucial remark. Okay. It just tells me how to create new derivation from known ones. Okay. And it said, suppose that you have D, which is a derivation. Okay. All right. Actually, a derivation, let's even say over Z, any derivation, doesn't have to be an A derivation. Then, so this would be over Z. Then if I connect it with this ring homomorphism, and it doesn't have to be A, it could be any. Now I just take A, but any ring homomorphism that goes to R, then, and I do, first I go from A to R, and then I go from R to M. So I'm doing phi, D after phi, when this is a derivation from A to M. So you get a new derivation, just first component is with the ring homomorphism. Okay? And this could be any ring homomorphism. When the second says instead, suppose you have an R modular homomorphism, so from M to N, okay? By the way, this doesn't have to be A, as I told you, could be B, any guy you want. Then, now what do I want to do? I first want to do D, okay? And then I apply phi. So phi after D is going to be a derivation from R to N. Okay? And even if this is an A derivation, I have even an A derivation, it's still true. This is going to be an A derivation. Okay? So this tells you how to create new derivation from old ones. And now let me talk, as I promised, about the modular differential. So what are we going to do with the modular differential? We're actually going to give 3 different definitions. Okay? And they're all important, and they all lead to different consequences. I'm going to just tell you before which 3 definitions we give, and then I go through them slowly. So the first one, I'm going to prove a universal property. That's very important because you know very well, when you get universal property, you know that the object is unique to isomorphism. The universal property is extremely important to prove it after something is a modular derivation. Okay, so this fact you have to really put it in your mind is, if you want to study anything about the modular derivation of differential, you have to know that. So we prove a universal property for the modular differential. Then, okay, we are going to give a actual description in terms of generators and relation of the modular differential. At least when you have an algebra essentially finite type. But even in general, I'll give it even if I have an algebra essentially finite type, I even give a presentation matrix of the modular of differentials. Okay? So really explicit that you can work with. And third, I give a definition of the modular differential through the diagonal ideal. So through the enveloping algebra. And that's also extremely important. So I give these 3, and you can get from each one of them a lot of mileage. So let's start with the first one, universal property. So this is the modular differential, okay? In a certain sense, you don't even know it yet what it is. I'll define it through the property, so it's very strange. So let's see where we are. So we have R and A algebra, as before. Okay? And so first we claim that there exists an R module, which we call, as I called it here, omega AR, which is called the modular differential of R over A, and a derivation that goes with it. Okay? And the derivation, we denote it often with R over A, and it goes from R, and is an A derivation, to omega, such that, so what's the ideal? What is the universal property? That any derivation you have, d from R to L, has to factor through this, which is called the universal derivation. So this is going to be called the universal derivation, and this is the universal modular differential. So every derivation is going to factor through it. So let me write it down. So such that for any delta from R to M and A derivation, there exists unique R linear map, and the map goes from, let me call it C or phi, whatever I call it, omega A of R to N, such that you can obtain my delta simply composing this phi, okay, with universal derivation. Remember, this is a derivation because we are composing an R homomorphism with a derivation, so we get a derivation, as the remark that I told you was crucial before. So let's make a picture first. And as I said, this is going to be called universal derivation. And this often we call it the universal, but I always call it the modular differential, but it's also called the universal modular differential of R over A. Okay? Because it's the derivation from which you obtain everything else. Okay? And now it's also clear this fact. Why? Because you have a derivation, you can always obtain it through phi. Given every delta, delta is uniquely determined by your phi, by your homomorphism from omega to R. Okay? Exactly this one. So, I mean, in general, it's not R, because this is derivation R from omega to N, in general, okay? So I'm going to write it down after anyway, this fact. But it proves immediately the fact that the dual of the modular differential is the modular derivation. If you take M equal R. Now, part 2 says that part 1 determines uniquely. Oh my God. And this means uniquely really means up to canonical R isomorphism. So if you had another one, there would be an R isomorphism from omega to the next one, and there would be an homomorphism from the two derivations in the usual way. Okay? So this is clear. 2 is clear. Is the usual thing that you always do when you have this universal property. So I'm not going to go through it. But what's important is that we prove 1. Let me, as I promised, make a picture of this. I didn't make it. I want to make a picture of one. So it's always a picture is always very useful. I put R here. This would be our omega. And what we promised, so this is dr over A, our derivation. And what we promise is that for any derivation near delta from R to M, there exists a unique map here. So this is the unique map that goes here and is an homomorphism, that these are our modules, that goes from here to here, such that the diagram commutes. So if you compose these two, you get delta. Okay? All right. So let's go through, as I said, the proof of one. So I'm going to do the proof in 2 steps. The first step, I prove it when R is a polynomial ring over A. Even infinitely generated, I don't care. But I prove it first when it's a polynomial ring. And then I prove it when it's a quotient of a polynomial ring. So just any algebra. So if R, this is the first case, is A, and now I want to have as many variables as I want, so I call it xi with I in an index I. Okay? I don't want to assume very fine, assume very. So this is just a polynomial ring over A. And now we have to decide how to find this module. We said that there exists this module. How do we find this module? We have to define the module, and we have to define the DRA, universal derivation. And then we have to check that it satisfies what we say. Okay, and actually what I'm erasing now is going to be very important. Because if you remember, I did compute the modular derivation, at least in the case, and that will be the dual, so I computed it in the case of a polynomial ring. So in this case, we take omega as a free module. Okay? Omega is going to be free. And we want to give a basis. The basis of this free module, we call it dxi with I now. Okay? And then we take the derivation DRA, okay, so defined. It goes from R to omega to this module, to this free module. And what does it do? It takes a polynomial, f, infinitely many variables, but remember, since it's a polynomial, it can only involve finitely many variables. That's the point. Because it's a polynomial, only finitely many xi appear, and then I can take the sum of the partial derivative of f respect to xi times dxi. And this sum will be finite. Because most variables in f don't appear. So this guy is indeed, an element of omega, because it's a linear combination of dxi. Okay? And then, with the same proof I did before, you can show that indeed this is a derivation. Okay? I mean, it's very easy to show. And once you do that, not only is it a derivation, but it has, how does it act on xi? Is exactly, it gives us back our basis element. So the image of the variable is our basis element. So you look at variables here, and they go to finish in this basis. In particular, this tells us that this omega is generated by the image of R. You see, it's just given by the image of R. Because this is the basis. You just have to look at the DXI. They give you the basis. Okay, now we are not done. I just define it. Now we have to show the important thing is that this couple that I define this way, it satisfies universal property. So we have to check that given this particular omega with this particular R, for any delta, this diagram split. Okay? So let me show you that. Remember, what's really very important here is that this is free. So that's what makes everything easy in this case. Then we have to do the general case. So since omega, so first of all, let delta from R to N be any derivation. Since omega is free, okay, I can define an R map, so an R homomorphism, that goes from omega to n in which way? What do I want? I just have to send the generator of this, what I want. And I want to send them exactly, remember these are the basis element, in delta of xi, where delta is this. Sorry, this delta of xi. Okay? Because if I do that, I'm going to get the commutative diagram. Okay? So this is well defined. And now, because this is free, so we get that immediately. In particular, notice, what is delta xi? But remember that xi was going, in our case, to dxi. And now we are sending it to delta xi. But this is exactly our delta is. So delta is exactly the composition of P after the array. By construction, by the way it's defined. Okay? And this is for every I in our index set. Okay? But now, and why is this true? So let me explain it to you, because you could say you just showed it, you just know that these two are acting the same on xi. What did I prove before that, that third part when I want to tell you when derivation are equal, that I told you we use all the time? To derivation are equal if and only if they coincide on an algebra generating set, okay, of R. And the algebra generating set of R is xi. These two are equal for every I and I are equal. I didn't even write it. Let me write it like this. Indeed, delta xi is equal C after DRI xi for every I in I. So they are equal for in every generating set, in all the generating set of R. They act the same. They have a two-way derivation, they have to be the same. So you get this equality. Clear? Okay. So now we have to show something else. It's not enough that we produce the map. We have to show the weakness of the map. So we have to show that there was no other possibility to do it. And this is clear because omega is defined from the image of R. So there was no other possibility. That's the only way you could define it. Okay? Because any other map had to send the xi there. Okay? So we have to do the same. So uniqueness follows since omega is generated by the image of R. Okay, now I want to do the general case. I only did the case when we have a polynomial ring. Then make case. Okay? So assume R is an A algebra. So in particular, R can be written as the quotient of S over I, where S is like in the first case, is A xi with I. Okay? And I is any, any idea in S. Okay, so now what do we do? For S, we have a unique pair. We already did the work in the first part. So we know that associated to S, you have a pair. Okay? From this pair, I want to get a pair associated to R. So think about it. You have S here, and you can obviously map S into R. And here you have your beautiful omega AS with D that is well defined. I want to put an object here, and I want to have a map here. Okay? So, first of all, I want this object, my question mark, to be what we call omega of R. Omega R should be an R module. So what we could do right away is take omega AS and tensor it with R. We can do it. Okay? This is an S module, so we can just tensor it with R. So what do we obtain? We just obtain omega AS modulo, we are going modulo I omega. Okay? Or actually, we can even write, yes. Now let's write I omega. Okay? That's what we get. However, if I put this object here, this diagram will not complete. You'll have an epimorphic image. So I will be, if I put here omega AS modulo I omega AS, I have a projection, but I will not have an inducement. How can I have an inducement? Let's think about it. Let's think about our algebra scale. If you want to have, so this is a projection, this is a projection, you can call this projection P, and this pi. You look at the composition of these two. You want this to factor through. What do you need? You need that I is contained in the kernel. Okay, so just let's throw I inside. So what we do, we add di here. If you add di, this diagram will commute. Because start with I, what's happened to you? You apply the I, you go here, but when you project, it goes to C. So now it factors. Okay? So this is the correct way you should define it. Hence, omega A of R is simply omega A of S. And remember, you have to comodo I and D of I. Okay? So one way to write it is S D of I, if you comodo I, and I D of S. Why I D of S? Because remember that the omega is generated by D of S. So that's one way to write it, which is nice to remember. Okay? All right. It's really S D of I plus I omega. You can write it this way. So I want to prove that this works. And I really can just use what I said. You know, this diagram induced the bar. The bar is induced by D since I is in the kernel of pi after D, P after D. Okay? So, no problem. And now, we also get that this guy is A derivation, since D is A derivation. That's easy to show. And now we have to show that that map has the property we want, universal property. And now, you'll have to do some of this exercise also today in the set to prove a stuff as universal property. That will be required, so you'll get the exercise this way, and you'll remember it. So take delta from R to M, any A derivation. What do we know? Okay, now I'm going to use that one that I told you a crucial remark. I want to have an S derivation because for S I know that everything works. Okay? So I consider the following. I go from pi, from S to R. And then, so this is pi. And then I follow pi with delta. The composition is an A derivation of S. Okay? So this delta after pi is a derivation by remark before, crucial remark. I told you that's the way to compute derivation, to get new derivation from old one. Okay? So this is a derivation over A. So this composition is an element in their S to N over A. But now, for every element of their S, this guy is universal. So I can factor that through D. So by universal property of omega S, there exists unique a map phi like we did before that goes from omega s to m such that I get this first I do pi and then I do delta as first I have to do the derivation from r to delta and then the phi. Okay? So first you do big D and then you follow it from the phi by the property before. Okay? And this exists unique. Okay, that's good. But now, so we have this one. What we want to get, remember, we want to write delta as a composition of this D, of D bar. Okay? How do we do that? Then we have to show that they factor through this guy. Okay? And then everything works. So really what we need to show is again the vanishing on I. So let me show you this. So we have to show, see, to factor, D is defined at the level of this D is a map from S to omega. I want a map here. So we better show that this guy is 0 on this. And then you get a map here. So let's see. P after D, okay, of I is the same by this of delta pi I. But this is obviously 0. Pi I is 0. Pi goes from S to R, so pi is 0. See, here I goes to 0. So this is clear. Okay? So this tells us that phi of SDI is 0. This big thing that we define. Also, we know to show the other thing. We know to show that phi of, so here we have the SDI, the IDS. So, yeah, now we have to show the other one. That phi of SDI is 0. And why is that true? No, this was showed here. We have to show the other one. I'm confused. IDS. And then we factor is 0. Why is this true? But this one is I times PDS because phi is a map of S module, so the I comes out. But now, this guy is M is an R module. So this lies on N, and N is killed by I, okay, because it's an R module. So this is 0, since I is in the later of N, okay, because N is an R module. All right, so now this gives us that this is 0, so phi is 0 here, and phi is 0 here. So which means that phi factors. So this phi factors. So here I can put, because here I can go, since in the kernel of phi there is the stuff, you can go to omega of R and define a map here. Okay, and you have a map here. This is the projection, and this phi induces a map from here to here. And that's going to be our phi bar. So let me write it. Remember, this was our map P, the projection on the modular differential of S over the modular differential of R. Okay? And now let's put this fact together with this. what do they give us? We are going to put in the place of phi bar. So we get delta after pi is phi bar after p composed with. Okay, this is just a phi, not a phi bar. And this is phi bar. Okay? And now we also have, so this is, I want to remember that this thing is the same as d bar after pi by our diagram that I just erased. So these two derivations act the same on R. D bar after D. Okay? And we are done. Remember, the bar is exactly our dr of A. Okay? Because if you follow them with pi, you get the same answer. So restricted to R, they are the same. And we finish this. Okay? And this is unique again because omega is also defined by the image of D. Okay, of R. Yeah, so that's unique, like before. The unique follows like before. Okay. So so this is the modular differential. Okay? And this is the first definition. And we know the universal property. Let me see it. Time is done. I still have half an hour, no?
Yeah.
Thank you. Because I covered not enough. I'm sorry. You know, I would like to go a little further. Okay, so now I would like, because I really would like today to give the three definitions. So this is the first. Now I'm going to go to the second that I promised, the one in terms of generator relation. We will not complete. I still, at the end of the lecture, hopefully, I give you in terms of presentation matrix. But still, I want to have a polynomial ring in infinitely many variables, so it won't be as concrete. Okay, I want to do it for any algebra, So, so this is the second description, if you want. So first of all, let me again, as a corollary, which is obvious corollary, so it doesn't need any proof, tell you what I told you before, but you get the derivation of from R to M as the sum of omega of R into M. And so if you put R, this is a clear corollary of that. Okay, so if you put R, you get that this is indeed the dual. And this is clear from that theorem there. So I should, since there are many rings, I should put here an R. Okay? Everybody's aboard? Completely clear? Okay. Now, second description. The second description comes again as a corollary, if you want, of the universal property. And we could have done it the other way around. We could have first give this description and then prove the universal property, but this is fine. So what did I tell you that the modular differential is? We said that in the case of a polynomial ring, we know it is free and is generated by dxi. So omega s is free, generated by dxi. And dsa is simply what I defined before, is the sum on any f, you have to obviously tell limit in any f, is the sum of the partial of f times dxi. Okay? So this we understand very well, and this is a complete description, it's a free module, 3S module. Okay? We want to do it when, in the general case. So in the general case, what did we write before? Sorry. In the general case, R is F over I, and I, let's say now, is generated by Fj, J in a script set J. I'm not assuming that J is finite either, okay? So I am in this situation, and I want to say what the modular differential is. But I told you omega R of A is a quotient of this guy by what I call IDS plus STI. So let's express it explicitly. So this means I'm tensoring this over R. So first of all, this guy, which was free, should be obtained as, again, a quotient of a free module, because this was free. So this guy was simply the direct sum of S dxi. Okay? I and I. Now I tensor it with R. So I'm getting the sum of R dxi, I and I. That's clear, because I tensor with R. But it's not enough. You remember tensoring with R was not enough. I have to comodulo. This means you already comodulo F, obviously. Okay, so I already comodulo IDS because I call it R dxi. But that's not enough. I have to comodulo SDI. So I have to comodulo the image of this guy with D, with the derivation. But this is the way the derivation acts. So I have to comodulo the partial derivative of F. And that's exactly what I do. I comodulo each of the generator. I have to take the partial derivative. In general, actually, not of the generator. From here, I have to, the truth should be that I have to comodulo this guy for every F in I. Okay, every F. And obviously, you have to take a bar because you should take this in already, modulo R in I. Okay? So this is what I should do. And this is for every F in I, and this is all the variables. But now, fortunately, and this is easy to show, and that's what I'm going to show now, I don't have to comodulo everybody. I just have to comodulo the generating, the D of the generating set. So this would come immediately from here. Now this requires a proof, which is easy. I have to prove that, I want to prove that I just need to comodulo the Fj, the generator. Which, if I find it, is not going to be bad, okay? In infinitely, then it's bad, but if I find it, it's much better. So let's prove this. And obviously, the derivation is just the image of the derivation. It's the divide, like you saw before. So it's obviously defined. Now, this is the point I want to show, so let me show you this first. So let's see. So this is clear from before, but this is the important thing. So I want to take any F. Any F in I is a linear combination of Fj's. Let me call it lambda or whatever, Fj. Some coefficients. I have lots of them, but I don't want to be. I'll do it on each sensitivity anyway. With the sum of lambda, I don't know, lambda S. Okay? Fj. I don't know, I should have a lot of Fj. Okay, I'm doing a mess. Lambda J. Okay? I just have to look at each guy. Yes? Yes.
On the left direct sum that you have on the board, what is the index over this?
The index is the dxi. So the index is over R.
What about over the sum on the bottom fraction?
This is I and this is J.
On the left of that equal sign, on the other side. The sum on the left.
This is always I.
Sum in the quotient.
I'm making a mistake. Ah, this sum. This
Yes.
sum. Oh, this is just on you know the you have to take this is really just the definition is df. Remember? I mean, it's over the variable that appear in f, and I don't know, there are not n. You know, f is finitely many variables, remember? I mean, xi there are infinitely many, but this was well defined, that's why I cannot put the index here. It's a finite sum because are all the variables that appear in f. Okay? Is this clear? Because f is a polynomial, so you involve only finitely many variables. And this is the sum over that variable.
Does I occur in the bottom, the I that you're indexing in the direct sum, does it occur on the bottom there?
No, I shouldn't call it I. I understand now the problem. I put the same thing. This should be k and k. Okay? These are just the variable that appears in f, and this is the sum over all r. Okay, I understand what you're confused about. Okay? And these are just the variables that appear in f. Okay? In theory, you have to use all the variables that are there, but this is finite because there are all finitely many. Okay, so now let me explain you this. And as I said, d is any derivation is additive. So I'm going to just look at the partial of this lambda, so of lambda j of j, okay, modulo dxi. And what you have, so what do I want? I want that this is determined just by fj, by fj. And this is true because this would be in general lambda j bar, everything is bar, fj over dxi plus fj d of lambda j over dxi. Okay? The Leibniz rule. Because this is an element of R. Okay, so you have to do this. However, this guy is in I. Fj is in I. So fj bar is 0 in I. So this goes away, and so you just get lambda j bar delta fj, delta xi. So this tells me that the sum is simply the d of the sum, the delta of f, the d of f is simply the sum over the dfj. So I just have to kill the generator. Okay? Is this clear? Then I have to kill the generator. Okay, so now this description will be much more concrete when R is essentially a finite type over A, because you'll have finitely many variables, because, and the I will have finitely many generators. So I and J will be finite, and then you have a presentation. So I'll talk about this, and then I want to give you the third construction. So the third definition now. Okay? So, by the way, one easy case of this is when you have an hypersurface. So maybe I should at least give you that example, because that's very easy. When you have an hypersurface, what's going to be the modular differential? So let's look just at the case of a polynomial, a very, very easy case that you can play with, and then you'll have a problem to do at home to play. So let's just assume that S is kx, okay? So omega S is just generated by dx. And assume that R is simply kx over f. One simple guy. So what is omega R? Oh, sorry, this is S. Then is R the x? But that is not enough. I also have to go modulo the derivative of f, so f prime. That's it. Okay? So that's all it is. Now, so obviously it's isomorphic to R over f prime. So now, let me look at this would be f prime x. Let me write it correctly, it would be f prime x. So this is just isomorphic to this guy. Now I want to do the third construction. So I have again R is an A algebra. And I'm going to define, okay, the enveloping algebra. Which we call RE to denote enveloping algebra, and is simply R tensor R over A. Okay? Remember, it's an RB module, it acts differently on the left and the right. Okay, we'll talk a lot about this. And obviously it's an A algebra. So this is the enveloping algebra. And we consider the following projection from RE, we go to R. And this is a projection given by the multiplication map. So I take two elements here. You can also write as X tensor Y. And I send it to XY. Okay? And then we want to look, and this is obviously, is clearly subjective, because you can just take a one tensor X and get everybody. Okay? Now, this is not injective, that's clear, okay? Because if you take one tensor X and X tensor 1, they have the same image, okay? So we ask what's the kernel? And the kernel is the so-called diagonal ideal. So this is the kernel of this map, okay? So, and the diagonal ideal is, I mean, you have to show it. It's not difficult, but you have to show it. Is generated by the guy of the kind X tensor 1 minus 1 tensor X. The one that I told you are obviously in the kernel, okay? Is generated by this guy. And now I have this exact sequence, okay? So this is called the diagonal ideal. I mean, it's clear that this guy goes to 0. You have to show that everybody that goes to 0, every sum of, because this is a tensor of xi tensor where j goes to 0 can be factored this way. Just a trick. I can show it, or you can try in the exercise. Should have added in the exercise. Okay, so now what we want to prove is the following. We want to find a modular differential out of this. And what we claim is this, that the R linear map delta that goes from R to D modulo D square, okay, this is a derivation, okay, and is actually the universal A derivation of R. Okay? So this guy is DRI. That's what we claim. We claim that this guy is equal to DRI. So this guy is isomorphic to omega R over A. So D over D square is the modular differential.
This delta is just x1 minus 1.
These are the generating set.
No, but this delta, the small delta that we find.
I didn't tell you how it's defined, yes. So it sends x in this guy, 1 minus x, 1 tensor x, minus x tensor 1. But I have to give it to you on every x, and I tell you the image of delta is exactly this guy. And this is obviously D over D square. Okay? So maybe I didn't say that. Delta x, I didn't, so thank you very much. Remind me, is this guy. In D over D square. But if we claim that this is the universal A derivation, as I said, what follows immediately is that d over d square must be the modular differential. Okay, so this is the first description of the modular differential. You just think of it as this quotient. So we have to prove this. So let me prove it. I think I have 7 minutes, so I will not finish the lecture. I'll finish the lecture tomorrow. As usually, I'm always expecting to do too much. But at least I try to finish the proof. Okay? So, the point is that we want to show that this is a universal property. Okay? So we want to show that this pair is isomorphic, is naturally isomorphic to this guy. But remember that this guy is defined to the universal property. So it's enough to show that this guy has universal property. That will be enough. So first of all, what can we observe? Observe first that this fellow is an R module. This is not clear from here. This is an ideal in the enveloping algebra. How does this become an R module? Well, because I co-modulo the square. Remember that R is nothing else than RE modulo D. And this is killed by D. So this is an R module. So this is the first thing. Otherwise, it couldn't be the modular differential. Okay? And also observe that delta is a derivation, is an A derivation. So this requires that I write something, okay? So clearly is A linear because this is defined as an R linear map. Because R linear is A linear, okay? There is no problem. So clearly is A linear, since it was R linear. And so the only point, all we have to show is how it behaves with respect to multiplication. So let's take the multiplication. What is delta xy? The delta xy is xy tensor 1 minus 1 tensor xy. But I have to be able to break this. So you use a trick. You add inside x tensor y and y tensor x. Add and subtract it. So you have xy tensor 1 minus x tensor y plus x tensor y minus 1 tensor xy. Combine. And now you can group them together. From this one, okay, you can extract x and then y tensor 1 minus 1 tensor y. From this one, you can factor y and then x tensor 1 minus 1 tensor x. So let me write it. I have 4 minutes, so maybe I stop here after this and I prove the rest next time. I want to, you must be exhausted. So this is equal x, y tensor 1 minus 1 tensor y, plus, now this was the first one. This is the second that I took out, okay? But the first one is that I take x, I take y out. Plus y, so this would have been maybe the first one, and this is x tensor 1 minus x tensor. X tensor, I take the y out. Something is wrong. I put them the wrong way, no? Yeah, I think I didn't combine them well. I want to combine this with this. No. Okay, now I'm confused. Okay, this is x, y tensor x. That's okay. Okay, this is x, y tensor x. And this is x. This acts only at the first one, remember. So this is xy tensor 1. So this is xy tensor 1 minus x tensor 1. So xy tensor 1 is, okay, that's okay. And the first one. And this one instead is xy tensor 1 minus, and the other one tensor x minus y tensor x. Perfect. Okay? So you have it there. So, and this is really x, the y plus y dx. It works. Okay? Delta. It's delta. Okay? Okay, guys. And now, so we have an R module and we have an A derivation. We have to show that they have the universal property. Next time I show you they have the universal property. Okay? So thank you very much.
Questions for Claudia? So you discussed this activity of replacing like the polynomial ring S with a quotient.
Yes.
What about if I have, for example, R is an A algebra, but maybe I have a subring of A? So I'm thinking that the differential module is maybe a quotient of differentials over B or something.
Oh, we'll talk about this. How you know how if you have more than one ring, how this is functorial. Okay, how you can consider you have a map from B to A, for example. Okay, or you have a map from R to T, another ring, and A is inside R and T, and now the modular differential of R and T relates. Or if you have A and B, and now the modular differential of R over A or R over B relates. If you that's what you asked. Yes. We're going to talk about it next time. Well, I was part of this lecture, but, you know, how this construction is really functorial.
Is there another question?
So far, everything now is characteristic free, right?
Yes, so far it's characteristic free. I'm going to go to characteristic zero later on. Yes. I will have to go later on, because otherwise I have to talk about, you know, transcendental bases and separability, and I want to make it easier, you know, and so I take characteristic zero. Otherwise, you have to take the perfect field, and you know, so it becomes more complicated. You have to have a p-basis, I mean, you have to be careful. So I rather take characteristic zero, but that's just the next lecture. I'm still, this is characteristic three.
What do you think? Claudia again?
Nice to